Okay, so let's start. No? Can everybody hear me? Can I see that thumbs up? Okay, good. Okay, so we continue our discussion of bipolar junction transistors. Okay, there's a question, different method of submission for problem set 2. Wala naman, no? The only difference is I separated the bins for each of the problems because they might be farmed out to different correctors. Instead of just one bin, each problem has a separate bin. Okay? So I hope I answered that question. Okay, so we continue our discussion of bipolar junction transistors. So what I want to cover today are transistors as amplifiers. So BJT amplifiers. So there are three BJT amplifier configurations. These are called the common emitter, common base, and common collector. So the common terminal is with respect to the time varying AC input. So for a common emitter, you have the emitter is your reference, okay? And then your input is at the base, and then your output is at the collector. So that looks something like this, no? For your common emitter, okay, your input is your reference. Let me just do it this way, no? Okay, your input is your reference. Rather, your emitter is your reference. Your input is at the base, and then your output is at the collector. That is your common emitter. Okay. Then you have your common base. In your common base, your reference is the base. So let me draw it this way. Okay. Your reference is the base. Okay. Your input is at the sorry. Tama, no? Common base, your input is at the base. Your reference, your reference is at the base. Your input is at the emitter. And then your output is at the collector. Okay. And then for your common collector, your reference is the collector. Okay. So your reference is here. Your input is at the base. And your output is at the emitter. So those are your three configurations. Again, the common terminal is with respect to the time varying input. It's not with respect to DC, it's with respect to the time varying input. Later on, it's going to be clearer to you what we mean by that, no? Because your circuit for your time varying input and your circuit for your DC input are actually two different circuits. And then remember, we apply the principle of superposition. No? So your DC input, that is your biasing, then your AC input, that is your signal to be amplified. Okay, the common emitter amplifier. So we discussed a very simple common emitter amplifier earlier in the first part of this module. So let me redraw that again. So you have VCC, you have RC. Okay, so your emitter is your reference, and then V, capital IN, and then I have V, capital O. So this is a simple common emitter amplifier. Okay, you remember our improved NPN transistor model. Where we said that I sub C, this is now I sub C, is equal to I sub S e to the VBE over V sub T minus 1, okay, multiplied by 1 plus VCE over V sub A. Okay. Can somebody tell me what V sub A stands for? I just want to check whether you remember. What is V sub A? Anyone? Sigaw na lang ninyo, no? What is V sub A? Yeah, that's right. No, somebody answered on the chat. That's your early voltage. So this term here is to take into account the early effect. No? What is the early effect? This is the slight increase in collector current as your collector emitter voltage increases. Okay? And then this is the model derived from Shockley's diode equation. Okay, this quantity inside here is actually the proportional to the base current, and because your collector current is proportional to your base current, then you can also write your collector current in terms of this quantity with the constant of proportionality equal to your scale current, your transistor scale current. Okay. Now you have V sub O is equal to VCC minus IC times R sub C. That is just KVL applied from this point to this point. So this is VCC minus, okay, let's have R sub C here. Okay, then you have I sub S e to the VBE over V sub T minus 1. Okay, this is now your V sub O. Okay, so what does this do? No, this relates. Okay, so for the amplifier circuit, that I showed, VBE is equal to Vin. No? Vin, VBE is equal to Vin. Kasi ito yung VBE. No? So yung VBE equal lang sa Vin. So V sub O is equal to VCC minus IC RCIS e to the Vin over V sub T minus 1. So this relates the input and the output, or to the output. This relates the input to the output. In other words, for a given value of V sub in, we can compute for V sub O. So for a given V sub in, can determine V sub O. Okay, I'd like to ask you to do this para lang ma-exercise kayo in using your calculators, and also to test you on basic concepts. So let's assume these parameters, no? So let's say VCC equal to 10 volts. Let's say RC equal to 2K, 2 kilo ohms. Let's say V sub T is equal to 26 millivolts. And then let's make VCE sat equal to the silicon saturation voltage, which is 0.2 volts. No? So can you just do this on your own? No? And please do it. Please do it. So determine V sub O for, okay, VI equal to 0.4 volts, VI equal to 0.65 volts, and VI equal to 0.70 volts. Okay. So can you do this? Let's start with 0.4 volts. Okay, can you type in your answers? Ice of S. That's right, kulang, no? Wala palang ice of S. I forgot about ice of S. Ice of S equal to 1.5 times 10 to the minus 14 amperes. Let's start with 0.4 volts. No? Can you give me your answer for 4.4 volts? Okay, just do it through the chat, and when enough people have had their answer, then I'll confirm. Okay, I already have an answer. Isa pa lang. Okay. Okay, I have an answer from 2. Let's wait for 1 or 2 more. Okay, it seems the others aren't working on it. Okay, I have enough answers, no? Okay, those of you that gave me an answer, just shout it out, ano? Anong mode of operation at VI equal to 0.4 volts? Anyone? Sigaw na lang ninyo, no? Anyone, please. What is the mode of operation?
Cut off po.
Yeah, cut off, di ba? Which makes sense, no? Because V of I mean, if we were to consider the simplified model of the transistor, what would VBE be equal to if it is conducting? That would be 0.7, right? But yung VI natin, VN, not VI, no? Sorry, VN, doesn't even reach 0.7, no? So we expect this to be cut off. So your VO would be about 10 volts, no? If you try to do the computation, it would be 9.99 something, 999 something volts, no? So it's practically equal to 10 volts. Okay. What about at 0.65, no? So please make the computation for 0.65. Okay, I'm getting some answers now. Okay, good, no? Halos pare-pareho kayong lahat, ano? So at 0.65, my VO is equal to about 7.84 volts. No? Okay, so last, at 0.7. At 0.7. Okay, 0.7. So I have 2 answers now. Okay, 3 answers. Huwag niyo muna titignan yung chat, ano? Okay. I thought you'd fall into this trap, ano? Most of you. And you did, no? Okay. Can I ask okay, no? Si Danuel, she's the first to give the correct answer. Can you tell everyone what you answered?
0.2 po.
Yeah, and why is it 0.2?
In saturation po yung
Yes, no, that's the check that most of you forgot to make. No, remember that. Okay, as you increase V in, okay, you expect V's of O to become smaller and smaller. No? Habang lumalaki yung V in, lumiliit yung V's of O. Pero yung V's of O, hindi siya pwedeng lumiit to something smaller than VCE sat, right? Ang pinakamaliit na pwedeng value ng V sub O would be VCE sat, which is 0.2. In other words, if you get a value that is less than 0.2, that means your transistor is already saturated, and therefore the output should be equal to 0.2. So dito, V sub O is equal to 0.2 volts. Okay, what do I want to do? No, I want to reconstruct. Okay, I want to reconstruct the transfer characteristics. What did we say was the transfer characteristics? This is V sub O versus V in. So I want to plot V sub O versus V in. And we can do that by actually doing a point-by-point calculation. This is a very cumbersome way of doing it, but it's one way of doing it. So here we already have three values: 0.4, 0.65, 0.7. Okay. You notice that this is something very similar to what was given to you in your problem set. You were given input points, and then you were instructed to plot your output. Okay, I already did this. This is just repeated calculations using my calculator, actually using Excel. Okay, and this is the table that I got. This is a V in, V out versus V in for values of V in ranging from 0 volts all the way to 0.8. So the ones that I asked you to calculate 0.4, 0.65, 0.7, ito yan, no? 0.4, 0.65, and 0.7. Okay. Okay, you'll notice that here, from here to here, your transistor is actually cut off. Cut off, your collector current is practically equal to 0, and therefore your output will just be equal to your VCC. On the other hand, here, these three, you're at saturation. Your transistor is at saturation, and therefore, even if you increase your input, your output will no longer become smaller than 0.2. So here we're in the active region. Okay, and you can also see that here, no? So from here to here, this is cut off. Okay. And then from here to here, this is saturation. Okay. Your saturation voltage is about 0.2, and your cutoff voltage is about VCC. So you can see that in this area, from here to here, this is your active mode. Yeah. Now, what is your gain? Your gain, by definition, this is a rate in change of your output over the rate in change of your input. By the way, no, sorry, no, I labeled it dV out here, not output, dV out. So the rate in change of your output over the rate in change of your input. So out na lang to, no? Anyway, you can make the adjustments in your notes. Okay, which is approximately equal to delta V out over delta V in, evaluated at your point of interest. Note that this value changes depending on where you are in the curve. For example, what is my gain in cutoff and in saturation? What is my gain? Can someone tell me? Okay, when my transistor is in cutoff, what is my gain? Anyone?
Close to 0 po.
Yeah, actually, for all practical purposes, it's 0. No, your your output does not change with input. Also here, no? Your output does not change with input. So the only time you really have gain is in the active region. Okay, that is the only time that this quantity is not equal to 0. And take note that depending on my operating point, I have different values of gain. Okay, let me ask you a question. Where is my gain higher? Is my gain higher at this point? Or is my gain higher at this point? Just by looking at the curve, where is my gain higher? Is it higher up here or is it higher down here?
Yun sa may taas, sir?
Dito?
Yes, sir.
Think about it again. No? Your gain is the rate in change in output with respect to your input, no? So that is in effect the slope of the line at this point. Where will the slope be larger? Will it be up here or will it be down here? Medyo sinabi ko na rin yung sagot, ano? Okay. So your gain, okay, for example dito, what is your gain? Your gain is actually the slope of this line. No? Gain is the slope, right? By definition also, no? Gain is dV out over dV in. Okay, so at this point, you have a different slope. Okay, so where is the slope greater in absolute value? The slope is greater in absolute value here than here. In other words, as I move this curve, my gain changes, and my gain is greater here than it is here. Now, the assumption is this: if you are using your transistor as an amplifier, okay, then the input signal is not going to vary by that much. Itong V in will not vary by that much if you are using your this as an amplifier, and therefore within the variation at this point, okay, you can just assume that the gain will be constant. Just like here within the variation at this point, you can just assume that the gain will be constant. So that is the assumption. So actually, when you choose, okay, when you choose your operating point, one possible criteria is the desired gain. That is one possible criteria. Okay. Is the desired gain. Because I might choose an operating, if I choose the operating point to be here, then I have a steeper slope, and therefore my gain is larger as compared to choosing an operating point up here. No, of course, where did we say was the well, on ano no, yung parang rule of thumb, usually you want to choose an operating point somewhere in the middle because it will give you the maximum possible input voltage swing. Remember, that's one of the criteria for choosing an operating point. But if your input does not change by that much, so that for example, if you choose this as your operating point, your input does not change so much that it will go to saturation right away, then you might want to choose this point because it has a very high gain. So that's a possible criteria. By the way, no, just to give you an idea what gains we're talking about here. So let's estimate the gain at let's say from V in going from let's say 0.65 to 0.75. 0.66. Okay, so from, let's say, V in from, let's say, 0.65 volts to 0.66 volts. Let's just estimate the gain. So let's go to my table. No? At 0.66, the voltage is 6.83. At 0.65, the voltage is 7.84. So my gain, this is evaluated at V in equal to 0.65, no? Is equal to 6.83 minus 7.84 divided by 0.66 minus 0.65. 0.66 minus 0.65. No? I'm assuming that that is the approximate gain at this point, no? At V in equal to 0.65. And you'll notice this is equal to negative 101. Negative 101. So that's how big a gain you can get with your transistor amplifier. That's somewhere here. Okay, if you made a computation somewhere here, you're going to get even a larger gain. So those are the types of gains that you can get. Now, the gain is negative. Negative gain. So anong ibig sabihin uli ng negative gain? Someone? Anyone? What does it mean to have a negative gain? Okay, 100 tama, no? Nag-i-invert siya, 180 degrees out of phase. Okay. 180 degrees out of phase. By the way, no, this is not like an op amp where you can amplify DC. Here, your input signal has to be a time varying signal, and your gain is applied to that time varying signal. That's why we say 180 degrees out of phase or inverting. Okay, any questions with regard to the common emitter amplifier? Any questions? Let's now go to the common base amplifier. So let me draw again a very simple common base amplifier. So what did we say? We said that the base was going to be our reference, the emitter is going to be the input, and the collector is going to be the output. So we'll have VCC. Okay, let's call this RC. So my base is my reference. So from the perspective of your time varying input signal or your AC signal that is grounded, then I now apply my input to my emitter, and I get my output from my collector. That's your common base amplifier. Again, let's work out a relationship between V in and V out. So let's derive relationship between V in and V out. Same way we did with the common emitter amplifier. So we start with V out equal to VCC minus IC times RC. So again, this is I sub C, which is VCC minus, okay, IC. Again, what is RC? What is IC? IC is just the I sub S, okay, e to the VBE over V sub T minus 1, where this is now equal to VBE. Okay. The question is this. What is VBE in terms of VIN? Can I hear from someone? What is VBE in terms of VIN? Anyone? Okay, so I have some answers here. Tama, no? Tama yung mga sagot nyo, no? VBE is equal to negative VN. If you do a KVL from this point to this point, okay, you get 0 minus VBE minus VN is equal to 0. 0 minus VBE minus VN is equal to 0, or VBE is equal to minus VN. Therefore, what is my expression for V out in terms of VN? I'm just going to get now V out is equal to VCC minus RC ice of S e to the minus VN, because VBE is equal to minus VN. This is over V of t minus 1. Now take note, for my base emitter to be forward biased, my VN has to be negative. So for BE to be conducting, VN must be negative. If VN is positive, then my base emitter will be reverse biased and my transistor will be in cut off. Okay, so let's assume this is the same transistor. Same transistor. Okay, so VCC is equal to 10 volts, RC is equal to 2K. This time I won't forget ice of S. 1.5 times 10 to the minus 14 amperes. V sub t is equal to 26 millivolts. Okay, VCE SAT is equal to 0.2 volts. Okay, so again, I'm going to make you just exercise your fingers in your calculators. So let's compute V sub O for, okay, again, 3 values. Let's start with negative 0.4 volts. And then let's go to negative 0.65 volts. And then let's go to negative 0.70 volts. So kung ano man yung ginawa natin dito for the common emitter with the positive VN, we'll do here for the common base with negative VN. So can we start with 0.4 volts? Can you tell me what V out will be when VN is equal to 0.4 volts? V out, no? Sorry. V out. Okay. Okay, yes, that's right, no? So kapag hindi umabot ng mas maliit sa 0.7, more or less, no? Of course, it depends on the model we're using for the transistor, no? But you know that more or less, when the voltage does not reach for silicon about negative 0.7 or smaller, then this will not be forward biased, right? And so your transistor will be cut off because your collector current will be 0, and therefore your V out will just be equal to VCC, which is 10 volts, no? Okay, what about for negative 0.65 volts? Can I see some answers? What is V out here? Okay, I have the correct answer. No? Actually, this the same as what we computed before. This is 7.84 volts. Okay, dito sa susunod, medyo mag-ingat kayo dito sa 0.7 volts. Be careful in your answer here. What is V out equal to? Don't be afraid to give it a try. Say what you think. Okay, I got V in plus 0.2. Okay, I got 0.2. Any other answers? .2. Minus 0.5. Okay, I got the correct answer from one of you. The answer is minus 0.5. Okay, actually, yung sagot ng isa sa inyo, V in plus 0.2 is correct, ano? V in plus 0.2. You have minus 0.7 plus 0.2 is equal to minus 0.5. So that's also correct, no? Okay, why? What is going to happen here? Okay. So, yung ISOC natin cannot be negative, right? Or rather, no, maybe that's not the right way of saying it, no. Yung VCE natin cannot become smaller than 0.2. VCE cannot be smaller than 0.2. In other words, if VCE is already at 0.2, it will no longer change. It will stay at 0.2. Now, theoretically, the output voltage should be V in plus VCE. So this is in saturation, no? In saturation, your output voltage will be equal to V in plus VCE sat. Okay, where VCE sat is equal to 0.2 volts. Okay. However, okay, we cannot indiscriminately increase in absolute value V in. Hindi pwedeng basta-basta increase natin in absolute value yung V in, no? Because if you increase V in to way beyond the conducting voltage, you're going to be overdriving your base emitter, no? You think of it as a diode, no? Think of it as a diode, no? This is your base to emitter. Okay, so your diode characteristics look like this. Okay, where if this is silicon, this is about 0.7. That's about 0.7. What will happen if I apply a voltage of 0.8? What do you think will happen if I apply here a voltage of, let's say I apply a voltage of 0.8 volts? I'm trying to operate the diode at this point, no? You're trying to operate diode at this point. But my characteristic curve is only up to here. So what's going to happen, no? You're trying to force this characteristic curve to go up so high Kasi bago yung voltage umabot sa 0.8, ang taas-taas na nitong characteristic curve, your current will be already hitting what? No, going toward infinity already. That's what's going to happen. In other words, you're going to destroy this diode. That's what will happen if you try to operate your diode way beyond the supposedly the forward voltage of the diode. And that's what's going to happen also in the transistor. In other words, when this Vin is already for this particular example, when this Vin is already at negative 0.7, okay, theoretically you should no longer increase the absolute value beyond negative 0.7. No? Wag na niyong paabutin ng negative 0.8 or negative 0.9. Kasi ang nangyayari, you're already pushing the base emitter diode to operate at a very, very high current, which will surely destroy your transistor. So I just wanted to mention that. So anyway, I completed the plot. So these are your common base transfer characteristic curves. What I did is I plotted the output from inputs from negative 1.2 volts all the way to 0 volt. No? Rather, from negative 1 volt all the way to 0 volt. Pero like I said, actually hindi mo na dapat i-operate dito yan, ano? Actually dapat yung limit is about 0.7, no? Based on this example, the limit should be about 0.7, or the limit for silicon should be about 0.7, because here we're already overdriving the transistor. Okay. So what are our operating regions here? Here you are at saturation. Okay, here we are at cutoff. And then here we are in active. We are in the active region. Is my gain positive or negative? Can someone just shout it out? What is my gain? Is it positive or negative?
Positive.
That's right. It's positive. Because my slope is positive slope. No? In other words, for an increasing input, I get an increasing output. My gain is positive. Okay, just by inspection, no? These are the same transistor used in the common emitter. We use in the common base, the same collector resistor. Just by inspection, where is the absolute value of the gain larger? Is it in the common emitter or is it in the common base? Anyone? Where do you think the gain is larger? Is it in the common emitter? Is it in the common base? Just by looking at the curve. Remember, your gain is your slope. Your slope. Of course, the gain here is 0, and the gain here is 0. No? So we only have gain here in the active region. Anyone? Any brave soul? Ang tanong ko na lang ganito, may pagkakaiba ba sa gain? That's right, no? They look about the same. The gain looks about the same. They have the same gain. So the gain, the magnitude of the gain is comparable to the common emitter configuration. So your common base and your common emitter configuration have just about the same magnitude of the gain. Your common emitter has a negative gain, your common base has a positive gain. So those are some of the reasons why you might choose one over the other. Now, Another reason why you might choose one over the other, and this is something that you're going to learn later on, is because of the input impedance or the input resistance, the input impedance of the amplifier. This is the resistance or impedance that is seen by the input signal connected to the amplifier. But we'll study that later on. But in terms of gain, they have about the same gain, and then the difference that you now know is the magnitude, the sign of the gain. One is positive and the other is negative. Okay. Any questions with regard to the common base? Okay, let me now go to the common collector. Okay, common collector. My common terminal is my collector, and my input is applied to the base. My output is applied to the emitter. Now, I cannot connect my collector to ground because my collector is where I need to apply my supply voltage. So my supply voltage is going to be applied at my collector, and then this is the simplest common collector amplifier possible. So this is V out, this is RE, and my input is applied to my base. Okay, now this is all this is the only explanation you need to know at this point. With respect to AC signals, okay, a DC source is equivalent to ground with respect to AC signals. Again, no? With respect to AC signals in your amplifier, your DC source is equivalent to ground. No? This is something to do with the principle of superposition. The principle of superposition, okay, with respect to your AC circuit, you you reduce all of your DC sources to zero. When you apply superposition, if you're considering only your time varying component or your AC component, okay, then you suppress your DC sources. And to suppress your DC source, you actually replace it with a short circuit. That's why, from the point of view of AC, this point is actually equivalent to ground. No? So let me just write that down. No? This is effectively ground from the perspective of the AC signal. That's effectively ground from the perspective of the AC signal. Okay, so let's try to derive a relationship between V in and V out. No? What is V out in terms of V in? Okay, let's do that. Okay, V out is really V in minus VBE. Okay. Now we know that IC, this is IC, is equal to I of S, okay, e to the VBE over V of t minus 1. Again, we'll first disregard early effect. No, we'll disregard early effect, and we know that this is approximately equal to I of S e to the VBE over V of t under normal operating conditions. Under normal operating conditions. So we can actually now express VBE in terms of IC. VBE is equal to V of t ln of IC over IS. That's right, no? Over IS. Okay. Now, however, for large beta transistors, no, if beta is large, which is the usual case, then I of C is approximately equal to I of E. I of C is approximately equal to I of E. No? Remember that I of E is equal to 1 plus beta over, sorry, I of C, yeah. I of C is equal to 1 plus beta over beta I of E. No? So if beta is equal to, if beta is large, then 1 plus beta over beta is approximately equal to 1. But I of E is V out over RE. This is I of E. It's just your output voltage divided by your emitter resistance. So we can write VBE. We can now write V out. So that's from this equation. So that's from this equation. V out is equal to V in. Okay. Now what is VBE? VBE is V of T ln of I of C is approximately equal to I of E. So we can substitute I of E here. Okay, you have V out over R of E times I of S. Okay. So given a particular value of V in, we should be able to solve for V out using this equation. Can we do that? Can we solve for V out for a given V in? Can someone tell me? In other words, if I gave you this equation, no, and I gave you a value of V in, would you be able to solve for V out? Anyone? Anyone? Medyo shy kayo, no? You don't want to yes, no? I'm getting correct answers here. Yes, you can. And you're lucky because you have your calculator, right? So ano gagamitin nyo? Yung gagamitin lang nyo yung solve function. You actually can do it using iteration. And when I was a student, we had no choice. No? We had to do this through iteration. But you're lucky you live in this day and age where you can just enter this in your calculator and then use the solve function. So pwede. Given a V in, we can solve for V out. Okay. Now I did that. So I'm not going to go through this anymore with you in detail. No, we've done enough exercise for that. I did that. So given a V in, these are the various values of V out that I computed. No? So ano lang yan, no? That's just using this equation. By the way, no, this is assuming the same transistor. So same transistor as before. And the value of RE, I can't remember. Yeah, I might have used the same value of RE, no, 2K. RE equal to 2K. Okay, so I already did that. No? Now, note that when V in is less than 0.7 volts, okay, when V is less than 0.7 volts, I hardly have any conduction In fact, from V in from 0 volts to 0.5 volts, my V out hardly changes. No, it's only when V in is 0.7 volts that all of a sudden gumagalaw yung V out ko. So if you take a look at the output, so this is my output versus my input. Hanggang dito sa about 0.5, halos wala akong output. So here, this is cut off. And that makes sense because we said that it should cut in at about 0.7 and it does, no? At about 0.7, it starts cutting in. Doon na lang nagkakaroon ng emitter current, right? When it is about 0.7, and that emitter current will manifest itself as the voltage drop across your emitter resistor, which is your output. Your output is actually the voltage drop across R's of E. Okay, and that will happen until about 10 volts. So here, okay, this is active. Now, what happens if I increase 10 volts further? No? If I increase the input beyond 10 volts. If I increase input beyond 10 volts, okay, VCE SAT will no longer, or VCE will no longer decrease. And VCE will be equal to VCE SAT, which is equal to 0.2 volts. Right? And V sub O is VCC minus VCE. Right? Remember, this is VCC, this is VCE, and this is V sub O. So V sub O is VCC minus VCE, right? So this is just VCC minus 0.2 volts, which is going to be VCE SAT. So notice that pag mas malaki na yung input voltage ko sa 10 volts, in this particular case, my output now clips at 9.8. So here, this is already saturated. And if I draw the transfer characteristic curve, it's going to look something like this. Can somebody tell me, just by inspection, what the gain is in active mode? What is the gain in active mode? Anyone? Just by taking a look at the numbers, no? What does the gain seem to be in active mode? So remember, this is my active mode. That's right. No, that's right. Around 1. Around 1. Positive or negative? Positive, right? +1. In other words, my input, my time varying input is just reproduced at the output with exactly the same, how'd you say this? With exactly the same amplitude. There's a question. Jamie, can you repeat the question so everybody can hear?
Sorry. Why does the value of V out saturate at 9.8 volts?
Okay. Sige, we'll do that again, ano? Okay. So this is my circuit. This is V out. Okay. This is V in. This is VCC. As V in increases, okay, V out increases. And VCE decreases. Okay. So this is the value of VCE, right? As I increase V in, my V out will increase and my VCE will decrease. When your transistor is in cutoff, okay, what is the value of V out? The value of V out is just equal to when your transistor is cut off, the value of V out is equal to 0, right? Because in cutoff, right, you have no emitter current, you have no collector current, you have no emitter current, you have no voltage drop across your emitter resistor, and therefore V out is 0. If V out is 0, what is the value of VCE? VCE is just VCC. That is when the transistor is in cutoff now. Now, as you increase V in, from VCE being VCC, so initially this is VCC, it starts getting smaller and V out starts getting larger. Now, can V out grow indiscriminately large? No, it cannot. No? Because at some point, VCE will be equal to 0.2 volts. At some point, VCE will be equal to VCE SAT, which is 0.2 volts. And from that point onward, even if I increase V in, my V out will no longer increase because my VCE is already at its minimum value, which is VCE SAT. And at that point, my V out is just VCC minus VCE SAT. So it is just 10 volts minus 0.2 volts, which is equal to 9.8 volts. Did I answer your question?
Yes, sir. Thank you so much.
Okay. Okay, so anyway, you see here that the gain is equal to 1. No? Okay. Now, I did something here. Okay, I used a different model of the transistor. So here, in doing this calculation, I used the exponential model of the transistor. I used this particular model of the transistor. Okay. Now in here, in this third column, I used a different model of the transistor. I used the model of the transistor, which just simplifies things. It just says that in conduction, your base emitter voltage is equal to 0.7. So I just wanted to do this for comparison. So this is using the exponential model. This is using the simplified model where in conduction VB is equal to 0.7. Take note that my curve looks practically the same. And my gain is also equal to 1. So I just wanted to show you that I could have actually just said, okay, when conducting VBE is equal to 0.7, and I would have come up with practically the same results. Okay, so this is what you call, this circuit is what you call an emitter follower. So a common collector amplifier is also sometimes called an emitter follower. It's used as a buffer. When you studied op amps, you studied the op amp as a buffer. The buffer is a circuit that isolates the input from the load. So we usually use this circuit to isolate the input from the load. What the input usually sees is a very, very large load resistance that will not make the input smaller. That will not attenuate the input, and that's the function of your emitter follower. Are there any questions? Any questions? Okay, so those are your basic amplifier circuits, transistor amplifier circuits, your common emitter, common base, and common collector. How do you apply the input signal to the transistor? Okay, I'll just go through this very quickly. So usually you start with your biasing circuit. So for example, let's say we use the voltage divider bias. Voltage divider bias. No? Or sometimes we call this the self-bias. So how does the voltage divider bias look? Okay. So we took this up last time. So you have VCC, you have RC, RE, R1, and R2. Okay, so this is the circuit that you will use to establish your operating point. So this is to establish your Q point. In other words, where in your transfer characteristics, kumbaga, let's go back to the transfer characteristics, no? Where in your transfer characteristics will you be operating at when your input signal is 0? Okay, so that is your bias circuit which establishes that. No? Okay, if you have a common emitter amplifier, okay, where do you apply your input? You apply your input at the base, but you have to capacitively couple it. So your capacitor will act as an open circuit to DC, but will act as a short circuit to your input signal. So this is for your common emitter. Okay. What if it is your common base? So if it is your common base, I wish I didn't have to redraw this, but so this is RC, this is RE, this is VCC. Okay. If this is common base, I have to. By the way, this is my output now. No, this is my V out. This is V in. If it is my common base, I want to apply my input to my emitter terminal. Okay, so again, this is my biasing circuit. I want to apply my input to my emitter terminal. So I do it this way. This is now my V in. No? By the way, no, sorry. Just to be more accurate, this is now going to be V small I small n. No? V small I small n. Kasi ang i-apply na lang natin ngayon is yung time varying component, hindi na yung buong voltage. It's already the time varying component. But even if there were a DC voltage there, this will filter out the DC voltage. So what will reach the base is just the time varying component. So this is my V in and this is my V out. So this is my common emitter, this is my common base. Okay. And then the common collector will look like this. Okay. So this is the V out for my common emitter, and then this is the V out for my common collector. So this is for common emitter and common collector. If I apply V in here, I get my output at the collector, that is a common emitter circuit. I get an output at the emitter, that is my common collector circuit. So that's how you actually design or develop your transistor amplifier circuit. Just some notes. The method that I used in analyzing the various amplifier configurations, what I did was I did a point-by-point calculation using the large signal transistor model. So the exponential model which we used, IC is equal to IS e to the VBE over V sub t minus 1. That's actually a large signal model. We can use that with any value of VBE. So I got my my transfer characteristic using that. But what I had to do was I had to do a point-by-point calculation. Okay, and the reason why I had to do that is because it's a nonlinear model. Now, fortunately, that's not how you're going to be analyzing transistor circuits from this point onward. No? From this point onward, you're going to be analyzing transistor circuits using the small signal model and using linear analysis. So I'm not going to have to do a point by point and then getting delta V sub O over delta V sub I to compute for the gain. I'm going to be able to compute for my gain using my normal circuit techniques, using normal circuit techniques that you learned in 1, 2, 3. You learned linear analysis in 1, 2, 3, and that's what we are going to use. But you are going to apply this to the small signal model of the transistor. So there's a parallel to what we did with the diode. The small signal model of the diode, you can use nodal analysis, mesh analysis, what have you. You can also do that using the small signal model of the transistor. And that's what we're going to take up on Thursday. The small signal model of the transistor. Are there any questions? Any questions? Okay, so
Ay, regarding sir po pala sa ano po, dun po sa pasahan ng problem set 2, parang tinry ko pong i-open sir ulit yung UVLE, medyo nagloloko pa rin po siya. Magkakaroon pa ba ng alternative na ano, submission bin, like Google Forms po siguro?
nagloloko ang UVLE. I'm sorry, I didn't know that.
Ano po, mula po kagabi nag-try po kami. Tapos ngayon po tinry ko ulit, nag-ano pa rin po, nag-gateway timeout pa rin po siya.
Sige, just email me the solutions to your problem sets para lang may backup, please continue to try, pero email me the solutions to your problem sets, at least matanggap ko before the deadline, so that there's a backup with me already.
Thank you po, sir.
Okay. Any other questions? Any other questions? Watch out also for announcements, baka magbukas yung course ng backup submission bin like Google Forms. But just the same, email na niyo sa akin para sigurado may kopya na ako. Okay, so if there are no questions, I'll close the session as usual when the last person leaves. Thank you.
Thank you po, sir.
Thank you, sir.
You're welcome.